All right. Hello, everyone. Welcome back. All right. So here's where we are. Today is Tuesday, November 9th, day 24. So we're doing lesson 32, which is the last lesson in this part of lessons, part 4, lessons 24 through 32. Right. Now, in principle, I could have had lesson 32 be part of this last block, but it was more convenient to have this now, as you see, because the calendar works out very nicely. Lesson 32 is an introduction to hypothesis testing, which is really what we're doing over in part 5 over here. But we're introducing the ideas now in lesson 32. This is part of the homework for part 4, though. And this homework will be due Friday of next week, Friday, November 19th, the day right before Thanksgiving break over here. So we're going to finish discussing the topics for the homework today. Remember, Wednesday, November 11th is Veterans Day. Thank you to all the veterans. This is a holiday, so we won't have class that day. And then next week, we'll discuss the homework from lessons 24 through 32, this part 4 assignment. Also, this week, I do plan on working through the homework 2 grading as well. All right, and then 3 I'll probably be grading during the Thanksgiving break. All right. So any questions before we go on? Any questions before we get to lesson 32? Ideas of hypothesis testing. And again, feel free to put questions in chat. No class on Wednesday. All right. So let's begin. Let's begin.
Hi, everyone. In the last part of the course, we're going to talk about hypothesis testing. How do we draw conclusions about population parameters, such as these guys? Remember them? A population mean, a population standard deviation, a population variance, or a population probability or proportion. And later on, we'll also do tests regarding relationships between variables. And we're going to draw conclusions based on sample statistics that we gather from sample data. In lesson 32, we're going to talk about hypothesis testing using p-values. There are other methods, but we're going to focus on the p-value approach first. And we're also going to talk about the issue of what it means to be unusual. In fact, the measure for that is alpha, the significance level, which we'll define later on. Actually, alpha is one of what you could say will be 3 ingredients to a hypothesis test. What are the 3 ingredients to a typical hypothesis test? A null hypothesis, labeled H sub 0 or H naught, sort of a British flavor to that. H sub 1 or H sub A, which represents the alternative hypothesis. See, null and alternative hypotheses, and also alpha, which is going to represent the significance level. We're going to meet him formally in just a moment. We've seen him before. It was the complement of the confidence level before when we did confidence intervals. We're now going to meet alpha officially when we talk about significance level. And again, that's the measure for what it means to be unusual. And p-values basically measure how unusual sample data is under a null assumption. Okay, so let's go through all this in greater detail. Once again, a null hypothesis, denoted by H sub 0 or H naught, is an assumption that calculations are based on. Because given sample data, what are some key numbers that we're going to derive in order to make judgments about the null hypothesis and the alternative hypothesis? Well, in order to make calculations, we're going to assume that the null hypothesis is true for now, and we're going to base calculations under the assumption that the null is true. What's an example of a null hypothesis? The coin is fair. That's going to be a common example for a null hypothesis in our class. The null hypothesis will often say that the magician's coin, the coin that David Copperfield gives us, is in fact fair. And we can base calculations on that assumption. Now, in a hypothesis test, we're going to decide one of 2 things. This is literally the decision. The decision. It is part of the hypothesis test. You need to make a decision as to what you're going to do with the null hypothesis. Are you going to reject the null hypothesis? Or are you not going to reject the null hypothesis? In some ways, you can sort of think of this as guilty versus not guilty in a jury trial. We'll talk more about that. Now, in a jury trial, you never say that a defendant is innocent, right? There might be some evidence against a defendant, but you never say in a jury trial, this defendant is innocent. Yes, there is a presumption of innocence. That's a bit different. But it is never a verdict in a jury trial that you say that someone is innocent. Likewise, we will never accept the null hypothesis. We will never accept definitively that the coin is fair. Here's an idea, and I'll expand on this later. But here's the idea. Let's say that you flip the coin that David gives you, and it comes up heads 51 times out of 100 flips. So you see 51 heads in 100 flips of a coin. We don't know if it's fair or not. Now, it's possible that you might not reject the null, right? It's possible you might not reject the null. You may not reject the idea the coin is fair, but you're not ready to affirmatively accept it either, because based on this sample data, what's the most likely probability of heads? It's not 0.5, it's 0.51. We're just saying this could be chalked up to sampling error. So again, we never accept the null. Here's another example. Let's say that when we can go out to bars, public places, you're at a bar and someone comes up to you and says, hey, I'd like to go on a date with you. And if you say, oh, well, I'm not ready to reject you yet, I'll think about it. How would you feel if the other person says, thank you for accepting? Thank you for accepting my proposal. That's not quite what you mean. All right, more on that later. So basically, we live in a world where either the null hypothesis is true or the alternative hypothesis is true. Again, we denote this by H sub 1 or H sub A. It's your choice. And this will serve as the complement to the null hypothesis. You can think of the alternative hypothesis as everything that the null is not. So if the null says the coin is fair, the alternative says the coin is not fair or is biased. I'll put that in red. So here the alternative is saying the coin is not fair or it's biased. Okay. And again, we live in a world where either the null or the alternative is true. We're either going to reject the null or we're not going to reject the null. And although we never accept the null, we do sometimes accept the alternative. Sometimes accept the alternative. For example, if a coin comes up 99 heads in 100 flips, we're ready to really dump the idea the coin is fair. And we sometimes accept the alternative that the coin is not fair. So in the hypothesis test, we decide to do one of the following, based on sample data, and based on that elusive alpha I've told you about, based on the significance level as well. So based on the sample data and whatever alpha happens to be, we're going to reject the null hypothesis, in which case we accept the alternative, as I just said, if we have 99 heads in 100 flips. We sometimes accept the alternative, even though we never accept the null. And one way to remember this, we sometimes accept the alternative, we never accept the null. The null never gets love. The null never gets love. I'll really emphasize that. The poor null. The null never gets love. We never accept the null. We never accept the null. We sometimes accept the alternative. Because we're a bit too skittish. Okay, I mean, even if the coin came up heads 50 times out of 100, we're still a bit skittish about saying that the coin is fair. Because what we're saying is just that we might be open to sampling error. when we're not rejecting the null, we're just saying that we're open to sampling error. When we don't reject the null, all we're saying is that we're open to sampling error. The null never gets love. We never accept the null. So we either reject the null or we do not reject the null. We never accept the null. The null never gets love. So next, we're going to play a little game to help us think about p-values and then values for alpha.
All right, any questions before we go on? Any questions? All right, so we're looking at the anatomy of a hypothesis test. Okay.
Hi, everyone. We're going to play a little game. It's my idea of a magic trick. And in the process, we're going to introduce some pieces to a hypothesis test, and we'll talk about the concept of p-values, which is a measure of how unusual your sample results are, under the assumption that the null hypothesis is true. Okay, so let's say I go around. This would be back in the pre-virus days. I go around the room and I ask people to pick cards off the top of a deck of cards. So I'm walking around with my deck of cards. I ask the first person to pick up the first card on the top. The first person picks up that card, shows the class the card, and it is a red card. I go to the second person and I ask that person, would you like to pick up a card? And that person says, why, I'd love to. So the person picks up a card and we see another red card. It could be a heart or a diamond. Let's say the third person picks up the card eagerly and we see another red card. I go to the fourth person. The fourth person picks up a card, another red card. What a coincidence. Fifth person picks up a card. It's another red card. Wow, what a coincidence, huh? Sixth person picks up a card, and it's another red card. And this has happened to me before, right? Just an amazing coincidence that the first 6 students to pick up the first 6 cards on the deck of cards, and they're all red. Well, what do you think? What assumptions might you have made if you didn't know I was a smart aleck? What assumption might you have made about the deck of cards? What do you actually see? And what are you now thinking? Well, now, you might be thinking, well, it could be chance, right? Maybe it was a coincidence. Or maybe you're saying, hey, I stacked the deck, or I just brought out a brand new deck of cards. What, you accused me of stacking the deck? Yes, I did. In these little experiments of mine, it's a magic trick where I stack the deck. I realize that Penn and Gillette will not be very impressed with me. But yeah, that's my little magic trick. I've stacked the deck. Yes, I stacked the deck. How did you know? How did you know? Well, example 1. We will look at the top 6 cards of a deck of cards, or the students did, right? What are the hypotheses? The null hypothesis and the alternative hypothesis. So the null hypothesis, H sub 0 or H naught, is that the cards are randomly ordered in the deck. See, if I were playing it purely fairly, right? Fairly and competently, right? Then I would have walked into class with a randomly ordered deck of cards where there was no rhyme or reason to it. It was a random deck of cards, right? And if you just see a random deck of cards on a table and it's not a brand new deck, then you might assume that the cards are randomly ordered. That would be your null hypothesis. And as we saw before, in our probability unit, you can calculate things based on the assumption of a random order. The alternative hypothesis, H sub 1, is that the cards are not randomly ordered in the deck. So we live in a world where either the null is true or the alternative is true. Either the null is true or the alternative is true. But it's harder to base calculations on the alternative hypothesis because if I tell you that this deck of cards is not random, well, how would you base calculations on that, right? What exactly is wrong, quote unquote, with this deck of cards? So it's much, much easier to base calculations on the null hypothesis because under this assumption, we can actually calculate probabilities. And we can see just how unusual this result is by chance. And the p-value will be a measure of that. So what do we observe from the sample data? I went around the room. The 6 students picked 6 red cards from the deck. We observed that the top 6 cards are all red. That was our sample data. The first 6 cards were all red. And then here's where the computation comes in. How unlikely are our sample results under the null, meaning under the assumption that the null hypothesis is true, under the assumption of a random deck of cards? Under the assumption of a random deck of cards. The null assumes a random deck of cards. How unlikely is it that the first 6 cards would be red? Well, what's the probability that the top 6 cards are all red under the null? It turns out to be 1.13%. I'll give you a few moments to try to remember how we did this. You may forget exactly how we did this, but you vaguely remember how we do this. I'll give you a hint. There are 52 cards in a standard deck of cards. We're not doing the jokers. I guess usually in an election year, I'd call the jokers the candidates, Trump and Biden. Okay, so we're not going to include the jokers. We have a deck of 52 cards. Half of them, 26, are red. And by the way, we're sampling without replacement. So that does make our calculations a bit harder. And 52 is not that big. So we cannot rely on like the polling assumption of independence. Do you remember how we calculated this? Well, what's the probability that if you really have a standard deck of cards, that the first card is red? What's the probability the first card is red? It's 1/2 or 26 out of 52, right? Hint, hint. So now assuming that the first card is red, conditioned on that, what's the probability the second card is red? You see the pattern? Here we go. It's a review of probability theory. The probability that the top 6 cards are red, given that the null hypothesis is true, under the assumption that the deck of cards is in fact random. The probability that the first card is red is 1/2 or 26 out of 52. Given that the first card is red, we have 51 cards left in the deck, 25 red cards left. The probability the second card is red, given the first card is red, is 25 over 51. The probability the third card is red, given that the first 2 are red, well, 50 cards left, 24 reds left if the first 2 are red. So the third probability is 24 out of 50, and so forth. We count down the number of cards left in the deck. We count down the number of red cards left in the deck because we're assuming that we're always getting red cards these first 6 times. Work this all out, we get about 1.13%. And that's a measure of how unusual it is to get the first 6 cards being red if you have a random deck of cards, if the null were in fact true. So we can think of 0.0113 here as a p-value, a probability that describes how unusual the sample results are under the null. Kind of like before when we talked about confidence levels. How sure are you that mu is in the confidence interval? Here we're asking, how unusual is this? We're being a bit rude. How unusual is this? Our p-value, 0.0113, is a measure of how unusual this is if the null were true. A lower p-value means more unusual. So for example, if you had gotten 10 red cards in the first 10 cards picked, that would be even more unusual. That would have an even lower p-value. So what do we decide to do about the null? The null hypothesis said, remember, the null hypothesis said that the deck of cards is random. That's what the null hypothesis says. Null says the deck of cards is random. The lower the p-value is, the more unusual the sample results are under the null. So for example, here, there is a 1.13% chance that you would see that the first 6 cards were red. The null said the deck of cards was random. So what are you inclined to do with that assumption? Reject it or not reject it? The null says the deck of cards is random. Based on these results, are you inclined to reject the null or not reject the null? If you think this is low enough, and many people would, if you think this is low enough, you would reject the idea of a random deck of cards. The lower the p-value is, the more unusual the sample results are under the null, like the 6 red cards, or say 99 heads and 100 flips of a coin, if you assume fairness. And the more likely it is, we will reject the null and therefore accept the alternative. So here's something that Triola and others came up with. It's a nice mnemonic or memory device. If the p-value is low, the null must go, as in go away. Not go as in green light, not that. If the p-value is low, the null must go away. If the p-value is low, the null must go away. We're inclined to reject the null. So if the p-value, 0.0113, is too low for the null to survive, to hold up, so this is like overwhelming evidence against a person's claim of innocence, for example, then we reject the null. That is, we reject the assumption that the cards were randomly ordered in the deck. Later on, we'll refine the wording of this. So how low is too low? What is that threshold under which, if the p-value is too low, we reject the null? That threshold is called alpha. And we'll talk about this fish thingy in just a moment.
Okay, actually, we're going to do something with tails first.
Hi, everyone.
Any questions? Any questions? We're going to look at some variations on this. All right.
We're going to talk now about the difference between a one-tailed analysis and a two-tailed analysis. In our 6 red cards magic trick, that was a one-tailed analysis because we saw 6 red cards and we asked, so what was the probability of getting 6 red cards among the first 6 cards just by chance with a random deck? But then someone might argue, but now wait a minute. If you want a measure as to how unusual that is, shouldn't we be fair? Shouldn't we also use symmetry? You can make the argument that we should consider not just the probability of getting 6 red cards in the first 6 cards, but also the probability of getting 6 black cards in the first 6 cards. That would be a two-tailed analysis. And it really depends on the structure of a test. You are going to see both one-tailed and two-tailed hypothesis tests. And there are related one-tailed and two-tailed p-values, especially when there's symmetry involved. So in example 2, we're going to revisit the 6 red cards example, but we're going to calculate the p-value differently. We're going to use a two-tailed analysis to get a two-tailed p-value. In example 1, the earlier magic trick, we calculated a one-tailed p-value because we focused on the probability of the top 6 cards being all red. I'll put that in red. Actually, this should be in another color. Let's say blue. Well, okay, so I'll put red around one-tailed, right? In part B, we did a one-tailed analysis. Now, in example 2, we're going to do a two-tailed analysis, okay, where we consider the following. One could argue that it is more appropriate to calculate the probability of the top 6 cards being all the same color, whether they're all red or all black. We're using ideas of symmetry. And this would be a two-tailed p-value. So here, we're looking at the probability that the top 6 cards are the same color, given that the deck of cards was truly random. That's still our same null hypothesis. Well, we take the probability that the first 6 cards out of 6 are red, given the null. That was 0.0113, 1.13%, roughly. Okay, and we add to that the probability that the first 6 cards are black. Because of the symmetry between the red cards and the black cards, it's the same probability. It's 0.0113. So the total p-value, the total two-tailed p-value, and this is often the case when we calculate two-tailed p-values, we take twice the one-tailed p-value, we take twice 0.0113 by symmetry, and we get 0.0226, or 2.26%. So we have a different measure here. Is it too low? Is it so low that the null must go away? Well, it depends on alpha. If alpha is 5%, then we reject the null in both the one-tailed and two-tailed cases. Okay, so here's another way of calculating a p-value by using a two-tailed p-value. Wait, what's this idea of tails? I mean, we're talking about 6 red cards, 6 black cards. What's this idea of tails? Why tails? And we'll do that in the next video. Why tails?
All right, any questions before we go on? We're going to talk about coins. Any questions? Any questions? Okay, feel free to put questions in chat.
Hi, everyone. In the 6 red card examples we've seen, we talked about a one-tailed analysis where we calculated the probability of getting 6 red cards out of 6, and a two-tailed analysis where we calculated the probability of getting 6 cards of the same color, whether red or black, out of the first 6 cards. And we'll do one-tailed and two-tailed hypothesis tests throughout our class. But what's this deal with tails? Why are we talking about tails? I'm going to talk about this in the context of coins, but as a setup to that, when might you want to use this idea of tails in example 1 or example 2? Let's say that in the first 6 cards selected by the students, let's say that 5 of the 6 cards were red. 5 of the 6 cards. Would it be enough to just calculate the probability of 5 red cards or 5 black cards? I would suggest that you would need to consider the cases of 6 red cards and 6 black cards as well. I'm talking tails. If that's not clear now, let's talk about a coins example. Why tails? Why do we discuss tails at all? Example 3. Let's go back to the magician's coin. David gives you a magician's coin, and it's going to be flipped 100 times. Technically, the ingredients for the hypothesis test, the null hypothesis, the alternative hypothesis, and alpha should all be predetermined before you get your sample data. So we're waiting. A magician's coin will be flipped 100 times. Okay? So what is the null hypothesis? What is the natural default hypothesis assumption you fall back on that you can base probability calculations on? What should be the null hypothesis? The coin is what? The coin is fair. That's the null hypothesis. The alternative hypothesis, H sub 1, is that the coin is not fair or biased. What do we observe from the sample data? Let's say you now take David's coin, you flip it 100 times, and you get 59 heads out of 100 flips. This might take you back to when you did that pink extra credit sheet, right? When you were flipping coins. Let's say you got 59 heads out of 100 flips. That's our sample data. Now, here's where the probability comes in. How unlikely are our sample results under the null? Well, now, a lot of students might say, well, I guess I'd calculate what's the probability of getting 59 heads out of 100 flips. What's the distribution, by the way? What is the distribution in play here? If X is the number of heads you get when you flip a presumably fair coin 100 times, remember we base calculations under the assumption that the null hypothesis is true, under the assumption of a fair coin. What's the distribution at hand? It's a binomial. X would have a binomial distribution where n equals 100 flips or trials, and assuming a fair coin, which is what the null says, P, the probability of heads, would be 1/2. And again, a student might say, well, I guess I could go to Excel and ask Excel, what's the probability of getting 59 heads? Or use that wacky formula. Well, let's go to Excel.
Okay, and that was in this video. Okay, any questions so far? I'll do an Excel analysis here.
Okay, so we got 59 heads in 100 flips of David's coin. How unlikely is that? What are some ways that we could try to calculate a p-value? Well, now, if we're flipping a presumably fair coin 100 times, remember, we're assuming for now that the null hypothesis is true. That's how we base our calculations. If we flip a fair coin 100 times and we count the number of heads, x, then x will have a binomial distribution with n equals 100 trials and p equals 1/2, the probability of heads on a flip of a fair coin. So if in fact we have a fair coin, then before we flip the coin, we know that x, the number of heads, will have this distribution. And Excel can crank out these probabilities. These are very tiny, right? The probability you get no heads or exactly one head, very, very tiny. For example, this here is about 8 times 10 to the negative 31st. But here's the thing. We're asking about 59 heads. We actually got 59 heads out of 100 flips. So a student might ask, well, what's P of 59? What's the probability of getting exactly 59 heads? Okay, well, if we scroll down, we see that the probability of getting exactly 59 heads is about 1.6%. And you might go, well, gosh, that sounds very, very low. But I might argue with you, in fact, I will argue with you, that this analysis isn't really fair. Because think about it. If you flip a presumably fair coin 100 times, what is the most likely number of heads? What value for x? What number of heads here is most likely with the highest probability? It's going to be 50 heads. X equals 50 heads. But look here, even the probability of getting exactly 50 heads is not that high. It's not even 8%. It's just a bit below 8%. So I would argue with you that just using as a p-value the probability of getting exactly the number of heads you got, that's not really fair. That's not really appropriate, because even P of 50, the most likely number of heads for a fair coin, is not that high. So that's why we consider tail probabilities. It's not enough to look at P of 59. 50 is the most likely number of heads, and even P of 50 is not that high. It's not even 8%. So the fact that P of 59 is only about 1.59% or 1.6%, that doesn't tell me that much. Instead, I should look at a tail probability. When I say tail probability, please don't confuse that with the fact that a coin can come up heads or tails. I'm using the word tails in different senses here. All right. It is more appropriate to find the probability of getting at least 59 heads if a fair coin is flipped 100 times. That will at least get us a one-tailed p-value. So instead of just P of 59, I'm going to consider the probability that X is at least 59 heads. So I'm going to add together P of 59 plus P of 60, the probability of getting exactly 60 heads, plus P of 61, the probability of getting exactly 61 heads. These are disjoint events here, so I can add up the probabilities. In any situation, you only have one number of heads, and so on and so forth. And then finally, P of 100. You add up all these probabilities. And I claim that you'll get about 4.43%, 0.0443. In fact, I had Excel do that. I had Excel take these probabilities from P of 59. You get very close to 0 here anyway, right? But I had Excel add up all these probabilities from P of 59 to P of 100. Not that these really mattered way down here. But when you add up all those probabilities, bingo, we get about 4.43%, about 4.43% if you add up all the probabilities from P of 59 through P of 100. So this one-tailed probability, the probability of getting at least 59 heads, is about 4.43%. So that is one possible p-value you could use, but again, someone could object. Someone could say, just like with the red card, black card example, why not consider a two-tailed p-value? And different people would use different measures. By symmetry, we can add on the probability of getting at least 59 tails. Now, if you get at least 59 tails, if you want to use our Excel spreadsheet, it helps to know that at least 59 tails means at most 41 heads. We're assuming, again, for now, the coin is fair. We're assuming symmetry for now. That's why a two-tailed analysis might be appropriate. So if we do that, well, the probability of getting at least 59 heads is about 0.0443, or about 4.43%. Well, likewise, the probability of getting at most 41 tails is exactly the same, about 0.0443, or about 4.43%. When you add up.
I should have said at most 41 heads, and that's the same as, that's equivalent to at least 59 tails. That's the idea. There's symmetry. I'll go back a little bit.
About 0.0443, or about 4.43%. That's when you add up everything from P of 41, P of 40, P of 39, all the way down through P of 0. Although again, we get very, very, very close to 0 down here, right? All right, so this is the same probability as before. These two-tailed probabilities are the same. So the probability of getting at least 59 heads or at least 59 tails, that is at most 41 heads, okay? That's twice the 0.0443 we got earlier for one tail. It's about 0.0886 or 8.86%. So that's another way that you can get a p-value. This is the two-tailed p-value based on our result of 59 tails, or I'm sorry, 59 heads, 59 heads. But this two-tailed p-value considers the probability of getting at least 59 heads or at least 59 tails. You could have used a normal approximation, maybe with continuity corrections, and you could have found this on your own without using Excel in such a way. Here, I was being very detailed. I was very precise here, but you could have used a normal approximation, especially with continuity corrections. That's nice. So what do we decide to do about the null hypothesis? Literally, what's our decision? Do we reject the null or do we not reject the null? Well, it depends on which p-value we take. Do we take the one-tailed or two-tailed p-value? Bear in mind, that decision should be made before you even flip the coin. The decision basically as to whether this is a one-tailed test or a two-tailed test, that should be part of the design of this whole experiment before you even get your sample. Okay, but whichever p-value we have, whether it's one-tailed or two-tailed, and also how low is too low? In particular, what's alpha? Too low means you're less than alpha. The p-value is less than alpha. We'll talk more about that later. What do we conclude? Well, our conclusion will depend on our decision. And looky here. And this is why some journals and some articles in journals give p-values even more so than alpha, because different organizations might have different standard values for alpha. 5% is usually standard, but it's not universal. 5% is usually considered standard, but here's the thing. If alpha is 5%, 0.05 or 5%, if 5% or 0.05 is our threshold for what it means to be unusual, remember, if the p-value is low, let's say lower than alpha, then the null must go away. Well, if your threshold is 5%, then this one-tailed p-value is too low. But this two-tailed p-value is not too low. It's higher than alpha, so it wouldn't be too low. So if you take this one-tailed p-value, if you're doing a one-tailed test, you would reject the null hypothesis. The assumption of a fair coin would be rejected. If you take this two-tailed p-value, about 9%, well, for this value of alpha, you would not reject the null. and the idea of a fair coin is still viable. Alpha, this threshold for what it means to be unusual. If the p-value is low, the null must go. Lower than what? Alpha. We'll talk about that next time. Remember, a p-value is a probability of obtaining sample results at least as extreme, that's a tail idea, as what we observe, assuming that the null is true. This implies tail. It could be one-tailed or two-tailed, right? We're going to use either one-tailed or two-tailed analyses for a z distribution, a t, or a chi-square, but we're going to deal with one or two tails. A p-value is a probability of obtaining sample values at least as extreme as what we observe, assuming the null is true. That's the definition of a p-value. Alpha, we're going to talk about next time, the significance level.
So remember, the p-value, any questions, by the way, remember the p-value is a measure of how unusual sample results are under the null, under the assumption that the null is true, like the coin is fair. Question. We never accept the null. Yes, so we either reject the null or we don't reject the null. We can accept the alternative, yes. So if we reject the null, that means that we accept the alternative. So we can accept the notion the coin is not fair. Okay, I know that it seems like the whole process isn't fair, but we never affirmatively accept the null, but we can affirmatively accept the alternative. And again, I'll talk more about these ideas throughout. Okay, so we never accept the null, but we can accept the alternative. All right. So again, the p-value is a measure of how unusual a sample is under the null. So I thought this would be a good time to take a short video here. Okay, so what does it mean to be too unusual, like her, the Winona Ryder character? It means you're below alpha. Let's talk about that.
Hi, everyone. We're now going to introduce alpha, this fish-looking guy, the significance level of the hypothesis test, our third ingredient. Remember, the other two ingredients were the actual null hypothesis and the alternative hypothesis, H sub A or H sub 1. Here's the third ingredient, alpha, the significance level. And basically, it is the probability threshold for what it means to be unusual, for a p-value to be too low. Remember what we said earlier. If the p-value is low, the null must go, as in go away. If the p-value is too low, the null must go away. We reject the null. So we reject the idea the coin is fair or the deck of cards is random. What's too low? If the p-value is lower than alpha. If the p-value is lower than alpha, then the p-value is too low, the null must go away, we reject the null. Again, how low must a p-value be for us to reject the null, whether it's in the context of a one-tailed test or a two-tailed test? Lower than alpha. So before, in lesson 25, we talked about the confidence level of a confidence interval, and we denoted that by 1 minus alpha. So for example, if we had a 95% confidence interval, the confidence level was 0.95 or 95%, which meant that alpha itself, the complement, was 1 minus that, or 0.05. This was like the failure probability for the confidence interval. Remember, if we have, like on this Rossmann chance applet, if we construct a bunch of 95% confidence interval, in this case for P, where P turns out to be 0.5, so the coin was in fact fair, then about 95% of these confidence intervals, these 95% confidence intervals for P, will contain the true value of P, 0.5, which we know in this case, and about 5% will not contain the true value of P. Here, it looks like 4% of the confidence intervals failed, did not contain the 0.5, but 4% is pretty close to 5%. We expect that about 5% of the 95% confidence intervals will fail. And again, you can play with this Rossman chance applet. In different situations, you could get different percents. 5%, 6% failing, and so forth. 5% failing, and so forth. All right. Alpha is a failure probability that tells how likely it is that a population parameter, such as a population mean mu, or in this case, in the applet, a population probability or proportion, P, is not contained within a CI for that parameter. So like over here, there's a 5% chance that the confidence interval did not contain the true value of P, the 0.5 for the fair coin. Now that was in lesson 25. Now here, alpha is the significance level of a hypothesis test. And we'll see how this connects together with the last idea in just a moment. Alpha represents the threshold for what it means for sample results to be too unusual under the null for the null to survive. So for example, maybe you get something like 99 heads in 100 flips of a coin. Well, if you're assuming the coin is fair, it looks like your sample data is presenting pretty strong evidence that that coin is not fair. The p-value you're going to get is probably going to be too unusual for the null to survive. The idea that the coin is fair. Now, it's typically assumed that alpha is 0.05 or 5%. That is the standard. Just like 95% confidence levels were pretty standard for confidence intervals. And certainly, under that kind of a standard, then sure, if you get 99 heads in 100 flips, we would certainly reject the null hypothesis that says that the coin is fair, certainly under that standard. But under these standards as well, other popular values for alpha are 1% or 0.01, and alpha equals 10% or 0.10. It turns out that alpha would have to be ridiculously close to 0 for this to be liberal towards the null, for the idea of a fair coin to hold up under these conditions with that sample data. Now, the higher alpha is, the more likely the higher alpha is, the more likely it is that we will reject the null. Because if alpha is high, right? If alpha is high, if alpha is way up here, okay, then it's very likely that the p-value could be any number beneath it, right? So the higher alpha is, the more likely it is that the p-value will be below it, and the more likely it is that we will reject the null. Now we could say something like, if alpha is high, the null tends to die, because it's very easy for the p-value to be below alpha. But I don't want to give you too many rhymes. That could be too confusing. So let's remember this. If the p-value is low, the null must go, as in go away. If alpha is high, it's more likely that the p-value is too low. So in a way, a 10% value for alpha would be like a really tough judge. It's like, it's going to be very easy for me to call the null guilty. Whereas a 1% judge is far more lenient. A 1% judge would require a higher burden of proof, a stronger burden of proof to convict a null. So maybe you have your own personal significance level, your own personal idea as to what alpha should be. It's almost like one of those games at the carnival, right? Test how much you love somebody. Test your value of alpha. Test your value of alpha. All right. A magician gives you a coin and tells you that the magician's favorite side is heads. You flip the coin and you keep getting heads on this thing. So depending on your personal value for alpha, when do you start saying that the results are too unusual for the coin to be truly fair? And we're going to do a one-tailed analysis here. We're only going to consider heads. So let P of X be the probability of getting X heads in X flips of a fair coin. Again, under the assumption that the null is true. We're performing these calculations, we're calculating these probabilities under the assumption that the null is true. For example, what's P of 1? Assuming that this coin is fair, What's the probability that if you flip a coin once, you get a head on that one flip of a fair coin? Well, by definition of a fair coin, 1/2 or 0.5. Now, you have this coin in your hand and you're wondering, is it fair or not? You flip the coin and it comes up heads. Are you ready at this point to call David a liar if David claims that the coin is fair? No, no one would. You flipped the coin, it came up heads. No one would call David a liar if David claimed that his coin was fair, right? If you got a head once on one flip. But what if you flip the coin again? Bear in mind, you should decide on the sample size early on, right? But we're playing this game. You flip the coin again, and you get a second head. You get 2 heads and 2 flips. What's the probability of getting 2 heads in 2 flips of a fair coin by chance? It's 1/2 times 1/2. We're assuming what I word? We're assuming independence. The result on one flip has nothing to do with the result on the second flip. The probability of getting 2 heads in 2 flips of a fair coin, 1/2 times 1/2, or 1/2 squared. We can use exponents, or exactly 0.25 or 25%. Now at this point, if you flip the coin twice and you get a pair of heads, David claims his coin is fair. Although you know that if anything, he may have a bias towards heads. See, here's the thing. I want this to be a one-tailed analysis. This is why I'm doing this. Okay, now there's a 1 in 4 chance that a fair coin comes up heads twice in 2 flips. Would anyone be prepared to call David a liar if David claims his coin is fair? Not too many people, almost no one, right? Certainly these 3 people would. Imagine 3 people, it's almost like the judging panel on America's Got Talent. Imagine 3 people as judges here, and they're judging whether or not David really has a fair coin. The alpha value for one judge is 10% or 0.10. The alpha value for another judge is 5% or 0.05, which is standard. That is what most judges would use. Well, I don't know about jury trials, but okay, I'm talking about statistics. Most statistics judges would use 5% as a standard value for alpha. Maybe alpha is 1% for this judge. Alpha is 0.01. But for this probability of 0.25, you can think of this as a p-value, like a one-tailed p-value where we're focusing on heads, all right? None of these 3 judges would be prepared to call David a liar if David claims that his coin was fair. Now the coin is flipped a 3rd time. What's the probability of getting 3 heads in 3 flips of a fair coin? That's 1/2 to the 3rd. It's 1/2 times 1/2 times 1/2. That's 1/8 or 0.125 or 12.5%. David claims his coin is fair. Would anyone call David a liar? Well, maybe some people on earth might call David a liar, but these judges won't. Even this judge here, this judge maybe doesn't like David. Okay, this judge is already suspicious of David. So maybe this judge beforehand picked an alpha value of 0.10 or 10%. But even for this judge, that's toughest on David, 3 heads and 3 flips, that's not quite intense enough. That's not quite unusual enough, even for this judge. And it's certainly not unusual enough for these judges. These judges are going to require stronger evidence in order to call David a liar. Now, what's the probability of getting 4 heads in 4 flips of a fair coin, of a presumably fair coin? It's 1/2 to the 4th, which is about 6%. And at this point, ladies and gentlemen, this judge on America's Got Talent, this judge in our statistics class, this judge turns their back on David. This judge says, I'm sorry, David, I now call you a liar. David claimed, his null hypothesis claim was that my coin is fair. The coin is fair. The probability of getting 4 heads and 4 flips in a one-tailed analysis is about 6%. So if this judge's alpha threshold is 10%, this p-value of 6% is too low. The 12.5% was not low enough, but this is too much for the judge to bear. 6.25%, that's lower than 10%. The p-value is too low for this judge. If the p-value is low, the null must go, as in go away. The judge now calls this too unusual for the null to hold up, and at this point, the judge would reject the null hypothesis, the assumption that the coin was fair. So this judge turns their back. But what about the 5% judge and the 1% judge? They're not ready to turn their backs on David yet. They're willing to give David still the benefit of the doubt. The probability of getting 4 heads and 4 flips is about 6%. Well, hey, this judge is at 5%. This judge is at 1%. You're going to need stronger evidence to turn these judges. Let's say the coin is flipped again. We now have 5 heads and 5 flips. The probability of that happening by chance for a fair coin is about 3%. And at this point, this judge has already turned their back. This judge now turns their back. By the way, it takes some time to get used to this. I use the term there now in a singular context. I used to not do that, but nowadays there is now preferred in some sense, even in a singular case. Anyway, this 5% judge, they turn their back. This judge says, hey, 5 heads and 5 flips, I'm now ready to call David a liar. So Mr. or Mrs. 10% judge, I'm ready to join you. I'm ready to call David a liar. But we still have this holdout. This judge at 1%, 0.01. This judge is not ready to call David a liar. 3% is not low enough for this judge. In fact, even if the coin comes up heads in a 6 flip, that's about 1.6%. That's still not lower than 1%. So this judge is still giving David a chance. But then at the 7th flip, all right, the coin has come up heads 7 times in 7 flips. That is going to be too much even for this 1% judge who might have liked David. So at this point, all 3 judges say, no, this p-value is way too low for all 3 of us. We're all going to call David a liar. And you are now off our show. This is too unusual even for the 1% judge. But still, hey, if you have a judge in principle who's at 1/100th of 1%, this isn't unusual enough. So you can keep going. Alpha has to be some positive value. In principle, if alpha is low enough, well, you'll still have some judges hanging in there. So it depends. It depends what the p-value is. It depends what alpha is. If the p-value is low, the null must go, as in go away. It's rejected. What's low? Lower than alpha. All right, the decision rule. Let's formalize that idea. Decision rules for hypothesis tests. And this is a literal term that is used in an advanced statistics class, a decision rule. The decision rule for a hypothesis test, using the p-value method. If the p-value is low, as in too low, as in less than alpha, then we reject the null. If the p-value is less than alpha, if it's too low, we reject the null. On the other hand, if the p-value is greater than alpha, then we do not reject the null. The evidence is not strong enough for us to reject the null and call David a liar. We're going to ignore the case where the p-value equals alpha because the probability of that happening is 0 anyway. And on homework or exams, I'm not going to pull that stunt on you anyway. The p-value that you end up with will either be less than alpha, in which case you reject the null. The p-value is low, as in lower than alpha, so you reject the null. The null must go away. Or the p-value is greater than alpha, in which case the null does not have to go away. We do not reject the null. Now we can also talk about a decision rule using the confidence interval method. We've been talking about alpha. How does this relate to a 1 minus alpha confidence interval for the parameter of interest? In this case, the parameter is p, the probability that David's coin comes up heads. What's the decision rule using the confidence interval method? Let's say that the null hypothesis states that the value of a population parameter is some value c. So in this case here, okay? The null hypothesis would say that the coin is fair. P equals 0.5. All right, develop a 1 minus alpha confidence interval for the parameter. It could be P, for example, the probability of heads. If this confidence interval does not contain the 0.5 from the null hypothesis, then we reject the null. For example, here, if our confidence interval went from, well, let's blow this up. If our confidence interval goes from 0.525 to 0.715, if the null hypothesis said that P was exactly 0.5, then if this 95%, let's say there's a 95% confidence interval, if this 95% confidence interval does not contain 0.5, the hypothesized value under the null, then we reject the null hypothesis under the standard that alpha is 5%. Okay, so again, if a 95% confidence interval for the parameter, remember, if we're saying beforehand that alpha is 0.05, which is the standard, right? If we're saying beforehand that alpha is 0.05, then 1 minus alpha would be 95%. So we're looking for a 95% confidence interval. If and when you construct a 95% confidence interval for P, your population parameter, the probability of heads, if that confidence interval does not contain the hypothesized value for P under the null, 0.5 in this case, since this confidence interval here did not contain the value for P under the null, 0.5, then we reject the null. We reject the idea that the coin was fair. Remember, the null is saying that the coin was fair. The null is saying that the coin was fair. Now, if the 1 minus alpha, or 95% in this case, confidence interval contains 0.5 in this case, then we do not reject the null. So basically, there's a 95% chance that your confidence interval will contain the true value for P if you do things appropriately, right? So there's a 95% chance that your confidence interval will contain the 0.5, like this one here. This confidence interval for P between 0.323 and 0.517. This does contain the 0.5, which is what the null said. The null said that P was 0.5, which means that we do not reject the null. It means that it's still feasible that David's coin was fair. We do not reject the idea that David's coin was fair. The null said P was 0.5. We got this confidence interval, which contained 0.5 as a possible value for P, realistically. So we do not reject the null. We don't dump the idea that the coin was fair. But again, do we accept the idea that the coin was fair? Do we accept the null hypothesis? And the answer there is no. I'll cross this out. We never accept the null hypothesis. We might not reject the null, like here, we might not reject the null. Maybe we got like 51 heads in 100 flips. Okay, maybe we got 51 heads in 100 flips, in which case we wouldn't reject the null. Still, we wouldn't accept the null because, well, actually here, the most likely value for P is 0.51, not 0.5. And even if this were 50 heads, we could still say, well, it could have been something else, but we're looking at sampling error. So basically, we get flaky. If we don't reject the null, we get flaky, and we say, you know what, P could have been 0.5, but we could chalk it up to sampling error. All right. So if we had gotten, say, 99 heads in 100 flips, we had gotten 99 heads in 100 flips, then it's likely that we would have rejected the null. The confidence interval would not have contained P. It would have been too high. The confidence interval would have been way out here somewhere. All right. Whereas here, the confidence interval would safely contain the 0.5 if we do not, and that's when we do not reject the null. Okay, next up is 59 heads unusual. 4 approaches next time. 59 heads in 100 flips.
Okay, any questions? Any questions? Doing kind of a wrap up of what it means to be unusual. Okay, some ideas behind part 5 of the class. All right,
next time. Hi, everyone. Let's get right to it. If you take David's coin, you flip it 100 times, and you get 59 heads in 100 flips, is that unusual? I wish I could give you just one response, but actually it depends on the analysis. It's more complicated than you might think. And we're going to use 4 methods to analyze this question. Is 59 heads on 100 flips of a presumably fair coin unusual? Or is that too unusual for the assumption of a fair coin to hold up? Remember, our null hypothesis is that the coin is fair. Or P, the probability of heads, is 0.5. The coin is fair. P, the probability of heads, is 0.5. In example 3, a magician's coin was flipped 100 times, and we observed 59 heads. The null hypothesis states that the coin is fair. Let's say that's David's claim. My coin is fair. The alternative hypothesis, H sub 1, states that the coin is not fair. These are complements. Use the significance level alpha equals 0.05, which is standard, but not always the case. So make sure you check on the value of alpha in the problem. Again, a hypothesis test has 3 key ingredients: a null hypothesis, an alternative hypothesis, and a value for alpha. Alpha you're basically given. The null and the alternative may depend on the way that the question is phrased. But for right now, it's fairly straightforward. The null says the coin is fair. We can base calculations on that. The alternative says that the coin is not fair. Do we decide to reject or not reject the null? Well, that's going to depend on if we use a one-tailed or a two-tailed analysis. It depends on what our value for alpha is, although I am telling you what value for alpha we're going to take. Different analyses will lead to different decisions, actually. And what do we conclude about the assumption that the coin is fair? What do we do with the null hypothesis? That assumption. We'll use 4 methods to answer these questions. Different methods lead to different decisions and different conclusions. Even for the same value of alpha, that could potentially happen. Method 1. For example, you could have a difference between your conclusions from a one-tailed analysis versus your conclusions from a two-tailed analysis. Method 1, let's use a one-tailed p-value. All right, so basically, what's the probability of getting at least 59 heads by chance? If you use, say, a normal approximation with a continuity correction, that's why you see 58.5 over here, then you find that this right-tail probability is 0.0443, or 4.43%. In fact, if you go to my Excel worksheet, that confirms this. So the one-tail p-value, the probability that X is at least 59 heads, because remember, if you get 59 heads, then it's not fair to just look at P of 59. You should look at the whole tail, right? Look at the whole tail. Add up all the probabilities from P of 59 through P of 100, which corresponds roughly to this area in here. Actually, the area of this is pretty close to the actual probability here, the sum of these probabilities. The area of this tail is actually a very good approximation. It is about 0.0443. Excel verifies that when it looked at the straight binomial distribution. Again, the one-tail p-value is about 4.43%. But now wait, is this too low? When do we reject the null? We're going to make a decision. Do we reject the null or not? Our decision. Do we reject the null or not? Well, the question we have to ask is this p-value low? Is this p-value low? What does low mean? Is it less than alpha? What was alpha? I'm saying in this problem, alpha is 5%, 0.05. So compare this p-value, about 4.43%, to alpha. So here's the p-value. And here is alpha. Compare the p-value to alpha. Is the p-value less than alpha or greater than alpha? Remember, I'm not going to have it be equal to alpha. Is the p-value less than alpha or greater than alpha? About 4.5%, that's less than 5%. That's less than alpha. So by this standard, the p-value is low. It's lower than alpha. The p-value is low. If the p-value is low, what happens to the null? The null must go, as in go away. We reject the null. We reject the null because the p-value is low. It's lower than alpha. By the 5% standard for alpha, we reject the null. That is, we reject the assumption that the coin is fair. So if I get 59 heads and 100 flips of David's coin, and David claimed, hey, my coin is fair, that's the null hypothesis, we're going to reject that assumption. We're going to call David a liar, basically, or he doesn't know. What about a two-tailed p-value? So 59 heads, is that unusual? Well, what does it mean to be at least as unusual as 59 heads? In method 1, we said that at least as unusual meant getting at least 59 heads. Now in method 2, we're saying that at least as unusual, here, at least as unusual as 59 heads. Okay, here in method 2, that's going to mean getting at least 59 heads or at least 59 tails when you flip this fair coin, presumably fair coin, 100 times. It's a two-tailed analysis. By symmetry, remember we're assuming a fair coin under the null. By symmetry, this left tail probability, getting at least 59 tails, okay, that's equivalent to saying getting at most 41 heads. Again, I have continuity corrections here. Well, we just double this right tail probability we got earlier. When you double 0.0443, okay, the probability of getting at least 59 heads or at most 41 heads, right? That's about 8.86%. Now, is that low? Is it too low for the null to hold up? Well, we're asking the question, is it lower than what? Is this p-value lower than alpha? What was alpha? It was 5%. Was 8.86% greater than 5% or less than 5%? It is greater than 5%. The p-value here, I know I say it right here, but the p-value here is greater than alpha. The p-value, 0.0886, is greater than our pre-specified value for alpha. So the p-value is not low. By this standard, the p-value is not low. Before, in the one-tailed analysis, we said the p-value was low, and we rejected the null. Here, the p-value is not low. We do not reject the null. And by the way, not low does not necessarily mean high. I mean, 8 to 9%, we're saying that's not low, but it doesn't mean that that's high either, right? For example, speaking of the dating scene, not ugly does not mean beautiful. So if you're being told that a friend of a friend is not ugly, you're not going to assume that you're going to get someone beautiful. Brad Pitt or Angelina Jolie. All right. So the p-value is not low. We do not reject the null. So we do not reject the assumption that the coin is fair. So if David says, hey, my coin is fair, you get 59 heads and 100 flips based on a two-tailed analysis. Based on a two-tailed analysis. Well, we have some evidence against what David is saying, but it's not strong enough. The p-value is not low enough. The p-value is not low enough. See, remember, a lower p-value means stronger evidence against the null. Lower p-value means stronger evidence against the null. I realize that's a bit confusing, which is why the null might be better. If the p-value is low, the null must go away. Here, the p-value is not low enough. We do not reject the null. We do not reject the assumption the coin is fair. We do not call David a liar. That might be a bad idea anyway, because he might turn us into a rabbit or something if he's really a magician. All right, anyway. Method 3, using a confidence interval. Remember, the null still states that the coin is fair, meaning the probability of heads, p, is 0.5 on the dot. I know that's not realistic, but according to the null, the coin is fair. P is 0.5 on the dot. The given value for alpha is 0.05. Please make sure not to confuse these numbers, right? Because you see a bunch of zeros and fives. Please make sure not to confuse these numbers. Alpha is 0.05 or 5%. So what kind of confidence interval do we want to look at? If alpha is 0.05, then 1 minus alpha is 0.95. If alpha is 5%, the complement is 95%. So we want a 95% confidence interval, or CI, for P, the probability the coin comes up heads. I had it up there, but I'll retype this. P is the probability that this coin comes up heads. For a fair coin, P is 0.5. That's what the null is saying. 0.5 is the hypothesized value for P under the null. I've never typed that. Let's do that. 0.5 is the hypothesized value for P under the null. So using methods from before, or maybe you're using Excel, a 95% confidence interval for P is given by this, from 0.494 to 0.686. Now, according to the null, P is exactly 0.5. Is 0.5 in this confidence interval? The answer is yes. 0.500 is contained in this confidence interval. It contains the value for P hypothesized under the null, so we do not reject the null. So what's a way of thinking of this? I don't know. If the CI is away from this 0.5, if the CI is away, the null goes away too. I don't know. If the CI is away, the null goes away too. Right? If the CI is away from 0.5, here the CI is not away from 0.5. The 0.5 is contained in the confidence interval, so the null does not go away. We do not reject the null. Okay, it's like one of these safe guys in green. That might be a way of looking at it. Green means safe. So on this applet, right, there's a 95% chance, if this is the true value for P, there's a 95% chance that the CI is good, contains the 0.5, green, right? If the 0.5 is contained in the CI, if you get one of these green confidence intervals, okay, green light for the null, we do not reject the null. We do not reject the assumption the coin is fair. So if David says the coin is fair, we're not ready to call him a liar. And by the way, this corresponds to the two-tailed analysis from above. So in fact, as far as the underlying theory goes, the two-tailed analysis from method 2 and this confidence interval method from method 3, which is in our class a two-tailed method, right? We have a tail to the left here, a tail to the right here. We get the same decisions and the same conclusions from method 2 and method 3. As for method 1, the one-tailed approach, maybe there could be a same decision and conclusion, but maybe not. Method 1 could give you a different decision and a different conclusion. But methods 2 and 3 are equivalent in the sense that you'll get the same decision and same conclusion from either method. Of course, for the same value of alpha and the same sample data. Method 4, this will take you way back, the 2SD rule for unusual z-scores. Remember, your sample data is unusual if it's more than 2 standard deviations out. It's not so unusual if it's within 2 standard deviations of the mean. All right. Again, from lesson 10, the 2SD rule for unusual z-scores. Z-scores that are either less than -2 or greater than 2, so you're too far away from the 0, the center, they're considered unusual, and the corresponding x values are also considered unusual. Okay, so on this number line for z now, on this number line for z, here's -2, here's +2. If you're outside, if your z-score is too extreme, then we're going to say that that's too unusual for the null to hold up. Right. If you're in between here, not so unusual. All right. So from before, we found that the mean was 50 heads. If you have 100 flips of a fair coin, right? 100 flips of a fair coin, all right? then the number of heads is approximately normal, where the mean is 50 heads, the standard deviation is 5 heads. For 58.5, that's after continuity correction. Don't worry, you won't have to freak out about continuity corrections on your last homework assignment. But the z-score for that is going to be 1.70, which is not an unusual z-score, right? 1.7 is safely in here, right? It's not an unusual z-score, so we do not reject the null. So we do not reject the assumption that the coin is fair. Now, here's the thing. If alpha is 5%, then method 4 will usually be equivalent to method 2 and method 3, but there's a bit of discrepancy there. Okay, so we have some of these methods that tell us that the null should be rejected. We have other methods that say the null should not be rejected. This is what drives pure mathematicians bonkers about statistics sometimes. We have 4 legitimate methods that yield potentially different decisions and conclusions. I'll tell you one thing that is not fair, though. I didn't even list this. It's the first method that a student would come up with. What's the probability of getting exactly 59 heads? But that's not fair to 59 heads, because even the probability of 50 heads is not even 8%. It's not that high. So the most obvious method, I don't recommend. It's not fair to 59 heads. Okay, in later lessons, we're going to formalize hypothesis testing and also how we're going to write that final conclusion. What can we say to the layperson? And we're also going to talk about the traditional approach to hypothesis testing afterwards.
Okay, fortunately, that will be after the Thanksgiving break. So it's going to be a big rush. Okay, look at this. We got lots to do after the Thanksgiving break. Okay, but we want to wrap these things up. And I wanted to give you this introduction to ideas of hypothesis testing. All right, so that's we're 9:34. Thank you for staying. I will stick around for any questions you have. On Wednesday, it's a holiday. I won't see you then. Have a good holiday. I'll be grading then. Next week, we'll be discussing this homework in great detail, both on Monday and Wednesday. And actually, I'm sorry. This is Wednesday. This is a Thursday. I apologize. That's Thursday. Okay, November 19th. Okay, I have to remember, you folks are Monday, Wednesday. So the homework is due Thursday, November 19th. And then Friday, you can just totally relax, hopefully. All right. Okay, any questions? Any questions? Otherwise, have a good night, y'all. I will stick around for questions. All right. Good luck on the homework. Any questions? Any questions? Okay, so at 9:37, I'll be back. I'll give you about a minute and a half to kind of wrap things up. Okay, so for many of you, have a good week. I won't see you until next week. I'll miss you. I'll be grading the homeworks. All right, I'll be back in a minute.